Hi, welcome to this demonstration of object classification. We're using a demonstration which is produced by a researcher at Stanford, and this demonstration is working with the MNIST data. The MNIST data is essentially some handwritten digits such as one might put on envelopes for old-fashioned physical mailing. And it's a moderately difficult task. There are only 10 digits. Think about how many potential objects there are in the world if we start talking about cats and dogs and planes and things we can see in the scenes around us. There's many, many more classes than in this data here. But it's a lot more challenging than the data that we saw earlier in the demonstration with the training that we saw with the TensorFlow demo. Having a quick look at what the demo shows you, there's a lot of statistics here about the progress of the training and the performance of the training. Some of these you should fairly easily recognize and interpret. For example, here it shows how long it takes to calculate the output when presented with an input. In this case, on this laptop, around 2 milliseconds. I hope in your laptop it's perhaps a little bit faster and not too much slower than this. And the backprop time is the time it takes to update all of the weights when you look at the discrepancy between the output that it should produce and the output it is actually producing, and propagate that error back through the network to update. Then we've got some statistics to do with how well the classification is performing. And the two very important statistics here is the training accuracy and the validation accuracy. And of course, it's the validation accuracy that we really care about, because this is on unseen data. It's saying how much of an error is being made on data that wasn't seen during the actual training process. The network has been training for a little while, and when we paused it here, it's already seen about 445 training samples. There's some parameters here to do with the learning rate, but actually there's a little complication here. If you read the fine print, these parameters are not actually being used at the moment in this demonstration. You can reconfigure it to use these parameters, but at the moment it's using a learning method that doesn't require these parameters. Underneath that, we have a section where it defines the structure of the network. And if you spend a little bit of time, you should be able to understand basically how to describe the network in this syntax used here. For example, if we pick this second line here, it's telling us that the start of the network is an input layer of size 24 by 24, because the digits are discretized into 24 rows of 24 columns of pixels. And output depth of 1, because it's a binary value. It's either a black pixel or a white pixel. Following that, we have what's called a convolution layer. And a convolution layer is the application of the weights to the previous layer, which in this case is the input layer. And the term convolution basically signifies that instead of a neuron in this subsequent layer having weights to every possible neuron in the previous layer, it only has weights to a connected patch of neurons in the previous layer. Then we have a pooling layer, and a pooling layer is basically one that takes a local average of the values that are presented to it, and this introduces a degree of shift invariance, so that if we shift the data a little bit, the output of this layer will still be roughly the same. If we have a set of numbers and we shift those numbers just slightly, the maximum value is still the maximum value in most cases. And this is a typical configuration of a deep learning network. It's a very popular configuration to have a convolution layer, a pooling layer, a convolution layer, a pooling layer, etc. This is not a particularly deep network. It only has 2 sets of these convolution and pooling layers, and then it has a final classification layer which produces 10 outputs for the 10 classes. It also produces, in this demonstration, some visualization of what the activation of the neurons are in each of these layers. And we can see that it's been presented here with a figure 8. And you can have a look at the output of the first convolution layer, and it's basically doing an edge detection on that figure 8 because it's basically producing very light or very dark, in other words, very high positive or negative, however you want to describe it, output values where there's a transition from the figure to the background. So it's basically detecting edges. The next set of layers is producing more complicated features from the data. It's producing things that respond to whole straight lines but not to loops, for example, in this particular section of it. And that's the whole point of training. It's for the network to learn what are the important shapes to focus on, working from the very, very simple shapes, combining them into more complex features for the subsequent layers to look at. Below that, we can see how the network is performing on the given test data. And remember, this network's not been trained very much, so it's not doing very well. The red bars are indicating where it's made an error, and the green bars are indicating where it's made a correct classification. And the length of the bars is essentially the strength of the output for that classification. So longer means that the network is more confident that that is the classification to choose. And these have been sorted so the largest one is on top, and then the second and the third, and the rest of the 7 aren't shown. The rest of the 7 possible outputs aren't shown. Okay, so let's train the network a little bit further. So we click the resume button, and the numbers are changing perhaps a little bit too rapidly for you to see them precisely, but you should be able to get a general gist of what the numbers are looking like. And we can see, for example, here the training accuracy is very high. The training accuracy, that is the accuracy on the data that's training with, is getting in the high 80s, low 90s. But the validation accuracy is a little bit less than this, and probably a little bit less than what you would like. The validation accuracy here is sitting around the low 70s, and now as the training is progressing, it's getting up into the low and mid 80s. If we were to let this train for a very long time, we can probably get to a stage where the validation accuracy can be up around 90%, but it'll take quite a long while. So I've paused the network again, and we can look more closely at the figures. We've got a training accuracy of 0.99, so it's doing almost perfectly on the training data. And we've got a validation accuracy of 0.9, so it's about 90% accurate on data that it didn't see. And if we go down to have a look at the classifications it's producing, you can see that it is still making a few errors. That's why the validation accuracy isn't 100%. But in the main, it's making errors where there's kind of an understandable reason for being a bit of confusion. This 3 here is a fairly badly formed 3 that kind of looks a little bit like a 2. And the 5 here is a 5 where the top part of it is merged with the bottom part here. And you could perhaps interpret that as a 3 or even an 8. Now there's a lot of things in this demonstration that we haven't touched upon that I encourage you to explore and to play with. For example, not had a look at changing the learning method so that we can look at the effect of these quantities such as the batch size, the learning rate, which you met in another video, and the momentum. The momentum is to do with when you are training and making your updates, you can play around a little bit by adjusting the learning rate to on the fly, step it back a bit if it looks like it's not learning too well, to make it a little less aggressive with the step sizes it's taking, and then to perhaps up that a bit if it's making good progress. And the momentum is basically, as in physics, basically saying how resistant you are to making those changes. If you put the momentum high, it will basically not make very large changes to the learning rate. If you put the momentum down, it'll be a lot more aggressive in trying to, on the fly, change the learning rate. Okay, a lot to play here. I encourage you again to spend roughly an hour or so playing with this and have a look at the effect of some of these parameters. Bye for now.